AP Calculus. Part 2 coming up. Just when you thought there would only be one derivative test. Dun dun dun. The second derivative test shows up. So, I really like the second derivative test because it shows whether or not you really have an understanding of concavity with respect to the intervals of increasing and decreasing. So think about this. Let's say you have a function that operates in this way. Let's just say it's got sort of like parabolic properties where it just kind of looks like a quadratic function. Now, what I can do is I can say, hey, this x value is probably going to be like an extreme value. So you take the derivative, find that 0. But instead of actually plotting it back into those intervals, what you can do is say, hey, I can take the derivative again. And if that critical number gives me a negative value, I know it's concave down at that point. Concave down means it's got to be a peak pushing everything down. So, you know what? Let me go through an example because I think I'm just going to kind of talk and it's not going to make sense. So, let's get a real example up there. So, you know what? I'm going to go from the handout. If you check out number 3, I'm going to use that function. So take x cubed plus 3x squared minus 9x plus 1. We'll say that's our f of x. And from your pre-calculus days, you know that if it starts with an x cubed and it's got a string of other x variables behind it, and the leading coefficient is positive, it's going to come from the bottom and it's going to move its way up. Now, it might move its way up a couple times, but we're keeping in mind that that's the general idea of what's happening. So we're going to have plenty to work with, at least one probably max and one min. So second derivative test says, I actually want to talk about concavity, right? Because if a potential peak is concave down, then that means you certainly have a max. So if the second derivative is less than 0, you have a max. Because a max would have to push the function down in order to be second derivative, in order for its second derivative to be negative. Conversely, all right, if the second derivative is positive, if it's concave up, you know that you should have a min value because it's got to be on the bottom pushing water up. So what do? Well, we first have to find the x values that actually would yield what those two x points would be. So step 1 for the second derivative test is I still have to find f prime. So 3x squared plus 6x minus 9 plus 0. Okay? And I'm still solving for the critical numbers. I'm still setting the derivative equal to 0 and solving it like normal. I can take out a 3. In fact, I can divide out the 3. It's a factorable polynomial. Plus 3 and negative 1 will create this product and this sum. What did I say? Plus 3 and minus 1? Yeah, that does it. So then our critical numbers are negative 3 and positive 1. But here's the kicker. Instead of setting up my intervals of increasing and decreasing, so I'm right, step 3, we're going to say no intervals. We're going to compute f double prime. We're going to take the second derivative. So from this point on, the second derivative would be 6x plus 6. And then you test the critical numbers that you got. So we're testing negative 3. And we're testing 1. So 6 times negative 3 is negative 18, plus 6 is negative 12. Granted, all right, so we're plugging it into the second derivative, which means getting a number that's negative would indicate that it's concave down. If it's less than 0, it's concave down. Concave down forces you downward, which means you have to have a peak in order to force something downward. And that's why we have a max. When the second derivative at a specific point, that's been confirmed to be one of the critical numbers from the first derivative. If it's less than 0, it's a max. If the second derivative is less than 0, it is a max value. Which, I don't know, computationally might seem a little bit backwards because it's like, well, I got a negative number, so now it's max. But hopefully that explanation makes sense, because if you understand concavity, concave down means I got to start from the top to move downward. All right. If you plug in 1 here, you get 6 plus 6, which is 12. 12 is greater than 0, which means if the derivative has tested greater than 0, you're concave up. So if it's concave up, it has to have a bottom to push upward. The bottom is the min. So we have a relative max at x equals negative 3. To get the original, you again would plug into, to get the y value, you plug into the original. So negative 3 cubed is negative 27. Negative 3 squared times 3 is going to be positive 27. Those two 27s cancel each other out. Then you get negative 3 times negative 9, because it's 0 minus 9 times negative 3. This ends up being 28. So it's got a relative max value at negative 328. And it's got a relative min value of 1. And if I plugged it back into the original up here, it'd be 1 plus 3 minus 9 plus 1. So 1 plus 3 is 4. 4 minus 9, negative 5. Plus 1 is negative 4. Let's check out one more example of this so you guys can kind of like start fresh from something with this concept in mind. And you're going to see like simple trig functions are actually, this is sort of like their bread and butter. At least I think so. Doing the second derivative test on those. So let's get a new fresh function on the whiteboard. Let's make it simple. Let's say your function is the cosine of 3x. And we're talking from, instead of from 0 to 2 pi, let's pick a different interval. Let's go negative pi over 2 to pi over 2. Let's just see how that goes. So second derivative test states you first take the derivative. This will be negative sine of 3x times 3. You have to find the critical numbers. You can't get around that. Divide out the negative 3 and you get 0 equals sine of 3x. So where are all the places where sine of 3x equals 0? Well, sine equals 0 at 0, at pi, at negative pi, at negative 2 pi, see, we got to think in terms of, we're in between negative pi over 2 and pi over 2, so potentially you're going to have some solutions that exist both at 0 and pi, but maybe also negative pi, negative 2 pi, negative 3 pi, 2 pi, 3 pi. And if you divide by 3, that'll tell us who actually does live in between negative pi over 2 and pi over 2. All right, so this is just going to be negative pi, which is out of bounds. Negative 2 pi over 3, yeah, that's further, so that's going to be out of bounds, which means these are also out of bounds. Okay, so negative pi over 3, 0 over 3, and pi over 3. So these are our critical numbers for our potential max or min values. So what do we do with that? Well, you take now the second derivative. F double prime of x is the derivative of negative 3 sine of 3x, which the derivative of sine is cosine. So it's going to be, come on now, we can do this. Cosine of 3x times 3 times negative 3. So there's going to be a negative 9 out front. So then we plug in negative pi over 3, 0, and pi over 3. F double prime of negative pi over 3, F double prime of 0, F double prime of pi over 3. And if you want to, you can use your calculator. You don't have to do this all in your head. So negative pi over 3 times 3 is the cosine of negative pi. The cosine of negative pi is going to be negative 1. Negative 1 times negative 9 is positive 9. So the fact that that's a positive 9 greater than 0 means my second derivative is concave up at a point that's potentially a max or min value. Because it's positive, it's concave up. It's concave up, which means it has to be a min value. If you plug in 0, the cosine of 0 is 1 times negative 9 makes it negative. Because the second derivative is less than 0, it's a pushing down. It's concave down. It's got to be a max value. And then pi over 3 yields cosine of pi, which is also negative 1. Negative 1 times 9 is positive 9. That's greater than 0, yielding a min value for making a concave up situation. Yeah, so then by plugging these two back into the original function, you'll find that negative pi over 3 and pi over 3 yield the same y value. They should both be negative 1. And then 0 gives us positive 1. So these are your two relative min values. This is our point of relative max. All right, guys. There was a lot going on in these two videos. I would encourage you guys to check out online resources. Just do a quick Google search or YouTube search of first and second derivative tests. I'm sure you're going to get a whole lot of people talking about those subjects because they're pretty fundamental in calculus. All right. Thanks for watching. See you later.